Okay, so yesterday you should have started learning about torque. I was out of the classroom a little bit yesterday, so that's why we were doing some CK12 stuff. So hopefully you got a chance to look at that in my absence. If not, that's okay. We're going to go over it. I'm going to give a short lesson today on torque. Kind of go over and reiterate what you should have read or watched yesterday, and then give you a chance to work on some torque questions. Okay, so what is torque? Torque is defined as the tendency to produce a change in rotational motion. Torque can also be defined as a product of the force and the lever arm that may cause rotational motion. So, the tendency to produce a change in rotational motion. So I'll stay consistent with what I was talking about yesterday for those in class. Imagine this is a door on a hinge. We'll pretend that's a good door, and that's a little doorknob right there. Okay, well, this is the hinge here on the left side, and the end of the door is out this way. Okay. Torque can be defined as that force you push with, right? When you go to open the door with the doorknob, when you push the door and cause it to turn about the hinge. So when you open a door, you're producing a torque. Or if you change a tire and you have a four-way and you're taking off a lug nut, you're producing a torque. Okay, now we can quantify torque with this equation. Torque, represented by the Greek letter tau, is equal to the length of what's known as the moment arm times the force applied perpendicular to the moment arm times the sine of whatever angle the force is being applied. Now, it says force perpendicular to the moment arm. So the force, and as you know, as you see with the door, you don't always push the door at 90 degrees. You don't always, open to hold a wrench exactly 90 degrees as you try to turn a nut. It doesn't work that way. So why the sine of theta? The sine of theta. That look back, by the way, this is the Greek symbol theta. This little, what appears to be a circle with a line through it, that means theta. Well, if here we have a lever and a force is being applied downward this way, the definition of torque says a force applied perpendicular to the moment arm. I'm just going to extend this out a little bit. By the way, this arrow here pointing at an angle is my force vector. So this is going to be an applied force. Now it says perpendicular. That's not perpendicular. Perpendicular means 90 degrees. For example, if it were perpendicular, this would be the force vector. This component, this here. But it's not. But what do you notice when I did draw a perpendicular force vector as a vertical component of the applied force, this original solid arrow here? Well, you see that it makes a right triangle. And this angle, the angle from the moment arm to the applied force, is theta. Okay, that's theta. So by trigonometry, we know that the side opposite of theta must be f sine of theta. I'm not going to go into that. That's prerequisite to this course. But that has to be f sine theta, this vertical component, because not all of this force that's at an angle is causing rotation. Only the component of the force that's vertical is and perpendicular to the lever arm is causing rotation. So that's where that comes from. Now, If the problem doesn't tell you it's applied at an angle, it should said a force is applied, assume it to be 90 degrees. So if it does not tell you the angle, if it doesn't tell you theta, if it doesn't say, okay, a force is applied at an angle of 45 degrees, for example, assume it to be 90. Okay, so here's a drawing of what a lever might look like and how to break it down. So here, this little circle on the left is a pivot point. A pivot point, or if you're familiar with simple machines from your elementary math classes, it's also known as the fulcrum. It's the point at which a lever rotates about. Okay. Now the moment arm is the length of the lever from the pivot point to the force, wherever the force is applied. That is known as the moment arm. Now, do not confuse this with the length of the lever. The moment arm is the length of the pivot point to where the force is applied. So let's look at this drawing over here to the right. Let's say I have a lever that is this long, right, represented by this horizontal line I drew. But the force applied is roughly halfway through the lever. It's about half the distance from the end of the lever to the pivot point. My moment arm is only going to be this far. Because as we go out, we're saying as we go out further from the center, we're saying that more torque is going to produce. Well, how do we know that? Well, you ever try to push a door from the hinges? It's pretty tough. But you go out to the end where the doorknob is, well, it's pretty easy. So this is our moment arm. Okay. And we represent the distance between the fulcrum or the pivot point to the force applied, or the length of the moment arm. We represent that with the lowercase letter r. Why an r and not a d? Well, like I said, this has to do with rotational motion. So if we were to push this and rotate it about that pivot point, r is going to be the radius of that circular motion. So we say that distance is r. Okay. So what unit is is torque in SI units? That is. Well, a torque is expressed in the units of Newton meters, right? We say it as Newton meters, and it looks like this: N dot M, or N times M. Generally has a dot. Okay, Nm, Newton meters. When the same amount of torque is applied to either side of the lever arm, then it is said to be in equilibrium. So let's say we have here like a seesaw, right? And we have two people of equal mass on either side. Let's say we have a mass over here and a mass over here. And let's say they're both 50 kilograms. And they're of equal distance from the fulcrum. Now, assuming the lever's mass is uniformly distributed, then this thing is not going to move. You're just going to stay there suspended on the seesaw because it is in equilibrium. So that's another thing to remember. If the torques on either side of the lever arm are equal, then it's said to be equilibrium. So torque on the left would equal the torque on the right. Keep that in mind as we move forward. Well, give me 1 second. Uh-oh. There we go. Okay. Over here on the other page now. So we also have this concept known as net torque. Now, all of this should be a review if you read the stuff from yesterday and watched the videos that were provided through CK12. So if it seems like I'm moving a little fast, it's because I am. Okay, so net torque is when more than one object is torquing a lever arm. Okay, when one or more object is producing a torque on a lever arm, we have to consider what's known as net torque. For example, let's say we have a lever and we have a force applied this way and another force applied. Let's say you and your little brother are pushing the door, right? This would be you, this should be your brother. Now, it may not seem like your brother is helping because you're probably going to produce a larger force, but y'all are actually both producing a torque on it. So to find the net torque or the total amount of torque that's acting on this lever here, you would take the torque that's being produced by you and add it to the torque being produced by the brother. And that would equal the net torque, similar to net force, right? When we have net force diagrams using, or when we solve for net force using Newton's second law. So a quick rule here. How did I know to add those together? Well, because we have this rule here that says torque causing rotation in the same direction are added together. So these two are going in the same direction. Y'all are both pushing from the same side, and you would add those together. But what about torques acting in opposite directions? Now, there's a couple of ways we could perceive this. Let's say we have a torque over here. Let's say we'll use a seesaw. Force of U, and I'm going to draw a bigger arrow over here. And the force of Mr. Lawson, because I'm big, and I'm going to produce a bigger torque on it because I'm a little more hefty. Okay. So my question to you is, which direction is this seesaw or this lever going to turn? Well, this one's trying to produce a torque and turn it this way, you on this end of it, and I'm on this side trying to produce a torque and turn it the opposite direction. Well, since I'm the larger force, it's going to want to go this way. It's wanting to go counterclockwise. But because you're acting on it in the opposite direction, it's not going to get the full amount of force acting on it. It's only going to get this little bit, right? Only that little bit of force is going to cause torque on the seesaw. So to solve for that, you take the torque of Mr. Lawson minus the torque of you when you go to solve for that. And that's how you find net torque. Okay. So here we go. Let's go to some practice problems here. And we'll see how this is done. By the way, you should have been taking notes. I forgot to mention earlier in the video, you should have been taking notes through that section. So if you didn't, go back through, rewind the video, and write down some important information you think you're going to need. I can also upload the PDF document that I used for this presentation as well, if you believe that will help you. That'll be on Google Classroom. So, okay, here we go. Getting to the nitty-gritty. So, number one, it says a force of 40 newtons is applied to a lever 2 meters long I won't say the end of a lever. Say the end of a lever. 2 meters long, how much torque is produced? Well, I'm going to approach these problems the same way I did the Newton's second law problems, by drawing a picture. I'll get it. Drew it too high up. There we go. So here I have a lever that is 2 meters long, and a 40 Newton force is being applied to the end of the lever. Okay? Now, I'm going to write my givens over here to the left. Now, I said force perpendicular because we're not giving it to be some angle, right? We're not said that it's applied at some certain angle, so we're going to assume it to be perpendicular and at 90 degrees being applied. Remember, because the definition of torque said a force applied perpendicular to the moment arm. So keep that in mind. We're also given the length of the moment arm to be 2 meters. So from here to here, 2 meters. And we're wanting to know how much torque is produced. All right. So next thing I want you to do is, if you're using a graphing calculator like a TI-84, something like that, we need to make sure that our calculator is in degree mode. I should have mentioned that earlier, but it just occurred to me. Degree mode, okay? You can do that by hitting second, mode, and then scroll down, I think 3 rows, and then there'll be 2 options. It'll either say radian or degree. Put in degree. Okay. Second, mode, degree. And make sure we do that before we continue. All right. So torque, we said, is RF. Ooh, that's not an F. RF sine theta. Right, that's our equation for torque. So R, we're given to be 2 meters. F is 40 newtons. And theta here is 90 degrees. So the sine of 90. Now, you may not know this off the top of your head, but if you put the sine of 90 into the calculator, it should come out to 1. Now, the sine of 90 degrees is 1. All right? So you know that by memory. And so if you go and put this in the calculator and you don't want to do that extra typing, we can just cross that out if it's perpendicular, because the sine of 90 is 1. Anything times 1 is itself. So this simplifies to 2 meters times 40 newtons. So our torque must be 80, and I remember our units, Newton meters. And that's it. Pretty straightforward. These 3 are going to be pretty decent, pretty easy. But we'll get to some more complex ones here in a second. So this one, it gives us a torque first. It says a 100 Newton meter torque is produced by rotating a 75 centimeter arm. How much force was applied? Okay, now again, it didn't give us an angle at which it's applied, but we'll do one of those later. So let's write down what we know. The torque is 100 Newton meters. R is 75 centimeters. Now, what issue do you see here? Well, torque is in Newton meters. This is 75 centimeters. Do you see a dimensional issue here? You should have nodded your head yes as you're watching this video. We need to convert centimeters to meters in order for us to get the correct answer. How do we do that? Well, we know that there are 100 centimeters and 1 meter. So we divide 75 by 100 and we get 0.75 meters. Okay, so be careful for that. Make sure we're working in meters. And just want to know how much force is applied, and we're going to assume theta to be 90 degrees. So we're just going to leave that out of the equation there. I did that again. All right, so here's my equation. Torque is equal to the length of the moment arm times the force applied. And sine of theta is 1, so I'm going to leave it off my equation. So R is 0. Actually, I'm not going to put in numbers yet. I want to solve for my missing value. I want to solve for F. Now remember, how do you undo multiplication? You divide, right? So we're going to divide both sides by R. So torque divided by R is equal to the force. So I'll put in what I know, 100 Newton meters divided by R is 0.75 meters is equal to F, the force. So now you got to remember to get out your handy dandy calculator and do 100 divided by 0.75. And that comes out to about 133. And it's wanting the force, so it'll be newtons. How do I know newtons? Well, we got a Newton meter here. Meters divided by meters cancel, and we're left with an N for newtons. And that's our force. Okay. Now this one's a little different. We have two people sitting on a seesaw. Now we don't just have one torque being applied, we have two. It says two people sitting on a seesaw. Mr. Lawson is a large human with a mass of 130 kilograms. Johnny is a tiny human with a mass of 50 kilograms. The seesaw is 4 meters in total length with the fulcrum at the center. If Johnny sits at one end, there we go. Yeah, there we go. If Johnny sits at the end on one side, where must Mr. Lawson sit relative to the center to keep the seesaw balanced? Ooh, there's a lot going on in this problem, isn't it? Yes, it is. Now, I'm just going to show you just how complicated these can get. But we'll take it one step at a time and think about what we know. And I think you'll realize that even though there's a lot of information here, it's not that bad. So here we go. There's my seesaw. We're said that Johnny sits at the end of one side. So I'm going to put Johnny over here. And Johnny we're given to have a mass of 50 kilograms. Notice it gives it in kilograms and not newtons. It's not a force. These are masses. Okay, these are masses. So I'm going to go ahead and say, write down what I know out here to the left. Mass of Johnny is 50 kilograms. And we're given the mass of Mr. Lawson, I'm going to say ML, is 130 kilograms. But I don't know where I'm at on this seesaw. We're trying to figure out where it is, where do I need to sit to keep it balanced? We're also given that the seesaw is 4 meters in total length, and the fulcrum's at the center. So R on this side is 2 meters, and R on this side is 2 meters. Or I'm just going to say the R of Johnny is 2 meters. I think that'd be better said. So R of Johnny is going to be 2 meters. All right. Now, remember in torque, when dealing with torque problems, we have to know T, we have to know R, and we have to know the force. Well, to break this down, right, to see what we need to do, we have to understand that this is a torque equilibrium problem. We have to think about net torque, right? Because we have to think about how to keep it balanced. And we have two torques acting on either side. We have this one acting on the left, and then Mr. Lawson's over here somewhere. We don't know where he's at. Well, how do I know what force is acting on it? Well, this kind of goes back to our free body diagrams. All right. Let's just look at Johnny. Let's look at Johnny for now. We'll get to Mr. Lawson in a little bit on his side of the seesaw. Okay. What forces are acting on this? Well, we have a normal force acting upward. I'm going to draw his free body diagram out here. A normal force acting upward that way, but we have his weight acting down. And the weight is what's going to cause the rotation. Okay, the weight's going to cause rotation. It's acting downward. It's going to rotate it down this way in this direction about the fulcrum. So the force of Johnny is going to be equal to the mass of Johnny times the acceleration due to gravity. Because remember, the force of gravity, or an object's weight, is mg, right? It's mg, mass times gravity. So let's figure out Johnny's torque. Okay, I want to break this up into two sections. I'm going to say, I'm going to put Johnny's work right here. The torque of Johnny, and we're going to assume it to be applied perpendicularly, is R of Johnny times the force that Johnny is applying. Well, we know R, right? R is 2 meters because he's sitting at the end of it. And the force we said was Johnny's weight, because Johnny's weight is what's going to try to induce motion, and rotational motion, that is. So we're going to say times its mass. His mass is 50 kilograms, right? And the acceleration due to gravity is 9.8 meters per second squared. We're going to assume I'm doing the seesaw on Earth. All right, so now let's multiply those together. Let's see. Actually, to make the math easier, I'm going to use 10 as my acceleration due to gravity. Just round it up, just to show you how to work the problem. Because sometimes you're asked to use 10, sometimes you're asked to use 9.8. It just depends on the problem and who's asking it. So 2 times 50 is 100. And that times 10 is equal to 1,000. So Johnny is producing a torque of 1,000 Newton meters. Now I'm gonna pause here and go back. Okay, I'm gonna go back and show you something. So let's look at this. When the same amount of torque is applied to either side of a lever arm, then it is said to be in equilibrium. Okay, you see that right here? Remember I told you that earlier? All right. We're trying to keep this thing balanced, right? So we know this is in equilibrium. We're trying to keep it balanced. It's in equilibrium, meaning in terms of net torque, it must be zero, just like net forces. If the net force is 0, then it's in equilibrium, right? Well, if the net torque is 0, then it's in equilibrium. So these are acting in opposite directions, right? I have John over here that's trying to induce rotation counterclockwise, and I have Mr. Lawson on the right side that's trying to induce rotation in a clockwise manner. So let's look. The net torque is going to be equal to the torque produced by Mr. Lawson minus the torque produced by Johnny. The net torque is 0, right? Because we're trying to keep it balanced. That's why I underlined it, trying to keep it balanced. So the torque of Mr. Lawson minus the torque of Johnny, is equal to 0. Therefore, to keep it balanced, we must be producing the exact same torque. The torque of Johnny is going to be equal to the torque of Mr. Lawson. So that tells us something very important. Because, look, it wants us to find out how far do I have to sit, right? So I need to find R of Mr. Lawson. Well, we know the torque I'm producing because it's the same as Johnny's. We solve for Johnny's. So let's look at the equation real fast. And let's think about what we got to solve for and then plug in what we know. Okay? And then I'll get back to what I was just saying. We're solving for R, right? We're solving for the distance. So torque divided by the force is going to be equal to R. Now, the torque is going to be the same as Johnny's, which is 1,000 Newton meters. We know this because it's in equilibrium. The force, just like John, I'm just going to put myself in an arbitrary location here with my 130 kilogram mass. The force is going to be my weight, because just like Johnny, my weight is going to be the force that's trying to cause rotation. So force, the force of gravity, is equal to 130. Now, the force of gravity is equal to mass times gravity, right? So I'm going to take my mass, 130 kilograms, and multiply it by the acceleration due to gravity, which I'm going to round up to 10 meters per second squared. And that's going to equal R, which is going to be our answer. So let's figure out what that is. Let's take our calculator, say 1,000 divided by 130 times 10, which is 1,300. And I get an answer of 0.77. This is about 0.77 meters. So what does this mean? This long drawn out problem is like, oh, this stuff just got difficult. Not really. We just got to break it down. But what does this answer mean? Well, that means if me and Johnny are sitting on a seesaw and Johnny's on the end of it at 2 meters, that means I need to sit 0.77 meters from the fulcrum in order to keep it balanced. Much different than Johnny. Because I produce a greater torque, so I have to go through to the center of rotation. Because I'm producing a greater torque, so to keep it balanced, you have to go through the center. If you don't believe me, go to a playground, take your little brother, your little sister, put them on the end of it, and you sit on one end. And what's going to happen? You're going to bonk the ground, assuming your little brother or sister is smaller than you are. You're going to hit the ground. So, and we've all seen it playing on the playground. To balance it out, what do? Well, you start shimmying towards the center. You start scooting towards the center, and then it gets easier to do the seesaw. So So yeah, that's our answer for that problem. If you had trouble, keep it following along. Just go back, rewatch it, and we'll figure it out. So anyway, let's think of another example real fast. I don't have this one written down, typed out, so I'll just go ahead and write it. Let's say a 30 Newton force is applied. Actually, how about this? Because I cannot write well when I'm doing these online whiteboards. So here we go. I forget that I can type it. Yeah. We'll say a 30 Newton force is applied at an angle of 30 degrees, 2 meters from, if I could spell, 2 meters from the fulcrum. Okay. I want to know what torque is produced from rotation. Oh, that was awful. But I have it typed out and we can see it. All right. So let's draw this out. Let's see what this looks like. So 30 Newton force applied at an angle 30 degrees, 2 meters from the, what the heck? Part of my problem disappeared. Hold on a minute. We'll get this figured out. What in the world? I'll tell you what. I ain't got time for this. All right. Well, I'm just going to draw it. From the fulcrum, what torque is produced? All right. So here we go. After all that, we have one final problem. Now I'm going to draw a picture. Here I have a lever, my fulcrum, and a 30 Newton force is going to be applied at an angle of 30 degrees at a distance of 2 meters from the fulcrum. What is the torque produced? Well, remember our equation. Torque is equal to Rf sine theta. R is 2 meters. F is 30 newtons. And theta is 30 degrees. So let's plug in what we know. It's a plug and chug type problem. We just got to make sure that we can identify theta. 2 times F, 30 newtons, times the sine of 30 degrees. So we put that in the calculator. Let me get mine. Now you may be asking yourself, well, Mr. Lawson, why don't we do the sine of the angle on the previous problems? Well, It didn't tell us that it was applied at an angle, so we just assumed it to be 90. Okay, but when it tells us it's applied at a certain angle, we have to put in the sine of that angle into our torque equation. So sine of 30 times 30 newtons times 2 meters. Uh-oh, I typed it in wrong. 2 times 30 times sine of 30. And I get, hold on, my calculator messed up. An answer of 30. All these 30s. But, well, that's because the sine of 30 degrees is 1/2. So that's why it come out to 30 Newton meters. So anyway, that's our answer. That's how you do it when you have an angle. Well, I guess I'll go ahead and end it there, despite my issues making this video. Let me know if you have questions. What I want you to do is complete your problems on CK12, and I'll also have some torque problems for you to work on in Classkick today. So good luck. Let me know if you have questions, and keep on learning.